So, hello everyone. Thank you for joining. I'm happy to see the room full. So today's session is about DataOps and data lakes. Before that, just a brief presentation of Kaizen. So Kaizen is one of the fastest growing companies in the game tech industry. We are present in 10 countries so far. What we are offering to our customers is sportsbook and casino games, and you probably know us by our brands, which is Betano for the international market and Stephen for the Greek and the Cypriot market. So about us, my name is Pantelis. I'm a big data engineering lead at Kaizen. 9 years of experience, 5 in big data. So I landed directly in the data lake world. And today we have Nikos also.
Hi, I'm Nikos. I have 5 years of experience, and I'm proud to say that I work on big data from the dark ages, from the age of Maroudis.
So today's presentation is about data. So first of all, do we have people here, or how many people do we have that identify as data persons? Just raise your hand. Cool, happy to see not many data people interested. So you're going to learn a lot of stuff. So from the data people, do we have people that work on data lakes? And do we have people that work with Databricks? Not Kaizen people working with Databricks? Cool. So in Kaizen, the way that we're structured is that we have these horizontal teams with a wide focus on providing services, processes, and data to the downstream users. And then we have these vertical teams with a specific focus on a component or a domain, and their goal is to provide value from the data. Nikos and I are part of the data engineering team, so our day-to-day life is to design and maintain the data lake architecture, and also provide the data, make the data available to the vertical teams. So Kaizen is growing, and the same happens with our data. So the data that we need to ingest and process every day grows at an interesting pace. The last 2 years, we've been doubling the data every year. But if you put that into perspective, it's not only the data that you need to process every day, but the data that you need to store. And there we have an even steeper line because of the cumulative effect that you have on storage. A part of that, there's also the number of tables that we need to update and maintain every day, which is also growing linearly. And this is because of the new use cases that we are adding every day to our lakehouse. And finally, we have the people that thankfully follow the same pace, and we've been adding new members to our architecture. That's all to say that it's not only the growth of Kaizen that not only reflect on the data, but also on the complexity of what we need to handle every day, and also the users. So these things are all aspects that you need to take care and you need to consider when you make your choices in terms of architecture. So now talking about the data lakes and what we believe the modern data lake architecture is, I'm going to take a step back and start from the beginning. So the beginning is the enterprise data warehouses. As some of you may know, they've been around for a while. They're designed to collect data from operational databases and support analytical workloads, so they're built for low latency and high concurrency. But one thing is that they usually come with a coupling of compute and storage, and especially when you have on-premise devices. That means that you have to provision and pay not only for the users that you want to serve, but also for all the data that you need to have under management. And this is a model that does not scale efficiently. In addition, you have proprietary storage format in order to achieve this high performance. And the most important for me, they do not support semi-structured or unstructured data, which are more and more in today's focus. So that's why we came to this two-tier architecture, which I think is the dominant architecture in our days. You have an independent file API for storing all your data. Then you have a secondary ETL in order to feed your data warehouse that will support the analytical workloads with the same level of service as the previous architecture. All the other workloads can just access the data from the storage. So this is low cost. It's based on low cost storage, especially with the rise of the cloud. You get very cheap storage and with high durability. You have open file format. It's up to you to choose what file format you can use, and you can host any type of data. But it's a bit of a complicated architecture. You have this two-step ETL that from one side increases your costs in terms of storage, and secondly, you have to handle the consistency and the lateness between the two layers of data. And last, all these workloads that do not use the data warehouse, they do not benefit from all these database management features like ACID transactions, indexing for performance, et cetera, et cetera. And this is where the lakehouse paradigm comes into play. The promise is that we'll eliminate the complexity, but we'll keep all the benefits of the two-tier architecture. How you do that? You provide a direct accessible storage, and on top of it, a layer that will add these traditional database management features. Again, ACID transaction, indexing, caching, all that stuff. Plus, it will bring the SQL, an increased SQL performance in order to support the analytical workloads. How this is done? There's two stars in this play. There is the Delta Lake. The Delta Lake will provide all these database management features and also reduce the I/O with your cloud storage. And this is one of the main bottlenecks of the architecture. And secondly, you have Spark that will take care of the SQL performance using all the features from Delta Lake, plus some extra internal implementations. And you have streaming that will deal with all the data lateness, and it's up to you to configure your reactivity. Our story is not very different from what I just saw. We started with enterprise data warehouse, ingesting operational data in a batch-only mode, processing them and putting them in a data warehouse, making them available for the analytical and the reporting workloads. So this is where we started. This is where we are now. We introduced new data sources. Now we support both batch and streaming for the ingestion. Our processing is based on Databricks, and it's built around Databricks. So Databricks is a platform as a service. It provides workspaces with, from one side, interactive notebooks, and on the other side, a managed service cluster, a managed cluster service. So we don't need to take care of spawning the cluster, terminating the cluster, etc. All is done automatically. Under the hood, you have Spark for data transformation, and MLflow for all the development and the lifecycle management of the ML models. Storage-wise, we are using the Azure Data Lake, of course using Delta Lake, and implementing this medallion architecture, which is the good practice in this kind of architectures. And on the other side, we keep this data warehouse in order to support all the legacy workloads that step by step we're migrating back to the data lake. So the end goal is to, at some time, press the button and turn off this data warehouse and stop paying for the extra resources. Now I'm going to pass it to Nikos for the DataOps part.
Okay. How many of you are familiar with the term DataOps? Okay, maybe DevOps? Some more people. Okay, you will learn a lot. Data engineering is just a specialization of software engineering. So we share many problems, and we have some unique of our own. As a data engineer, I deal with I have many complex teams that I usually work with, from DevOps engineers to BI experts to domain experts. So all these teams bring a different terminology, bring different tooling, different platforms, and cooperating efficiently may be a challenge. Also, all these teams have different cultures. Some teams are more comfortable with automation, with testing. Others are more comfortable with manual procedures. And the level of tech savviness may vary. Also, a data pipeline may be using many different and diverse tools, from ingestion frameworks, from message brokers, to transformation frameworks, to machine learning algorithms, to visualization tools. All these layers add different modes for failure and inherent complexity. Also, that's what is unique in data engineering is that data is tightly coupled with business procedures. So business procedures have this property that they are never stale, and they constantly evolve. Actually, if you build a data platform that enables data-driven decision-making, you accelerate the rate where the business procedure change. So by the end of a big development, maybe your assumptions about your data may have changed completely. So DataOps, as a term, communicates that is correlated with DevOps. It wants to achieve what DevOps achieved for software development, which is increase in quality and a decrease in lead times. DataOps takes from DevOps the focus on automation and integration. Also has two other supplementary frameworks that takes ideas, Agile software and lean manufacturing. Agile, when introduced in software development, has shown time and time again that reduces delivery time, especially in environments where the priorities are constantly shifting, which is a very well-known situation for us data professionals. Also from lean manufacturing, we take the idea for statistical process control. Lean was developed as a framework for the automotive industry in the 50s. And the focus is to eliminate waste and to have an automated way to monitor quality and to monitor the end-to-end process. These ideas that came from a line of work in automotive can surprisingly can be applied also in the software development. So this is the frameworks for DataOps. So there's not a single agreed definition what DataOps is. If you review many data professionals, you can get some components. But our attempt to give a definition is this: practices, processes, technologies that bring speed and agility end-to-end data pipelines. What we can all agree is that DataOps is not a platform that you can buy and install in your company. It's not a specific technology. It's not a specific team. It's not a step. It's rather a collection of principles and a way of doing things on a cultural, organizational, and technological level. So, DataOps extends the classic DevOps framework by adding some key elements. For example, sandbox management is something that is added, and it's a first-class problem, because you can't simply copy your data lake in a dev environment isolated for a developer to create new analytics. So that it is something that you need to take into consideration. The next steps, development, testing, integration, automation, are something that's common with DevOps. And some unique elements are also orchestration, where you need to take into consideration the intertwined dependencies of your pipelines, and also to have a way to deal with inevitable failures. Also, monitoring is the capabilities that you need to support for being proactive rather than reactive, in order to be alerted as fast as possible when something is out of place and things like that. In our view, DataOps can be dissected further into some collection of principles and some pillars that you need to support. So you need to support data governance, which means capabilities like metadata management, like data cataloging, and security in general. Also, we have architecture and processes. Process is the focus on how you deal with new code introduced in your code base and your code quality overall, which means integration, CI/CD procedures, and code reviews and things like that. And architecture is the focus on architectural components, especially on cloud with things like infrastructure code and things like that. And data pipelines refer to the capabilities we discussed as orchestration and monitoring. So we have some stories to present. I know that a lot of you have a background of software engineering. So version control and CI/CD are things that were available maybe decades ago, but data platforms hadn't have caught up recently. So, what are the requirements to have CI/CD and version control? Of course, collaboration. You need to have an efficient way for your developers to share on a common database. Also, you need to have a way to roll back on incidents. When something is released in production and you want to go to previous version, version control is a lifesaver. Also, you want to have a way for safely integrate new code into production. This means you want to eliminate as much as possible all the manual steps and automate everything. So, what was the starting point? In 2020, when this initiative rolled, the state was this. Databricks, for you who are not familiar, you can develop your code in something called Notebook, which has a look and feel like Jupyter Notebooks. This has a flavor of version control, which is embedded and accessible from the UI directly, and it's very intuitive. On the other side, no Git functionalities. This forces also the developer to copy your code in your local folder and then copy back to production, which is a difficult thing to do. Also, you're not protected against something going wrong, a developer going to the production notebook and then misclicking something and everything breaks apart. And also, if you want a CI/CD procedure, you have to manually do something custom. You need to download everything, to upload your Git repo, and then do the reverse order. In Databricks, Git integration was supported with DBR Databricks Runtime 8.1 in Q1 of 2021, and we decided to go with Azure DevOps as a product of preference. It offers all the Git features we know and love, PRs, commits, etc. And also it has its own version of CI/CD with build pipelines for integration part and release pipelines for deployment part. Also, it supports integration with third-party applications like Jira, Slack, and things like that. On the other side, we didn't at the time have the knowledge of this platform, so we need to upskill in that area. And also, we had some projects that we already use version control in GitLab. So the starting point looked like this. The developer developed local in his computer and then uploaded to GitLab, do the PRs and merging and things like that, made the local build and then upload the results on Databricks platform with the resulting jars. Also, for our ETL and orchestration and things like that, we developed directly on the Databricks platform and then we manually copy to the production, an error-prone procedure. What's our current workflow? Databricks is currently directly integrated with Azure DevOps, so you make your feature branch, and then you have a normal life cycle of CI/CD. You have the UPR validation, your build tests, and then when it's time to deployment, you deploy from the release agent straightly to the Databricks platform, and also you can upload your configuration jars into the data lake. So another problem that we need to solve was orchestration. What are the actual requirements here? We need to schedule at scale. Currently, we have at least 5,000 daily batch operations that we need to do, and many of these are small tasks. Also, you need to have a failure handling mode, and we wanted something that would be notebook-based, because we explained in Databricks you can develop in notebooks. So what were the options in this area? From more out of the box, Databricks offers a scheduling capability to manage services like Azure Data Factory and to unmanaged services and open source leaders like Apache Airflow and Luigi. Azure Data Factory was considered, and actually we have developed some pipelines there, but we opted out eventually because we wanted something that could be cloud agnostic. About Databricks, what was the state in 2020? You have a native scheduling capability, so you can create a job for each of your notebook. The pros here is embedded, it's accessible from the UI, and also it's very intuitive. On the flip side, no dependency management. It means that when you need to schedule a job after one another, you need to implement this manually. Also, no visual overview, so you can't deal with what's running right now and what are the dependencies. And this causes problem of unmanageable jobs because the number of jobs would increase with your tasks. Also, in the Databricks, for those who haven't worked on the platform, there's this duality about interactive clusters and job clusters. Interactive clusters can be shared by multiple notebooks, and job clusters spawn on command. So when they spawn, they have a setup time, which it's something that you want to eliminate. And job clusters are more cost efficient, so you want your ETL to run on job clusters. Actually, Databricks have worked on many of the things that we raised here. So it now supports multitask jobs, which handles the dependency part. You can define your DAGs, your direct logical graphs. And now comes with a visual representation, and also you can use a common job cluster, so you pay the time for the setup once, and then all the job runs on the same job cluster. On the other hand, you're missing some key capabilities. So you can completely run your DAG, you can't run only certain steps, and also you can't interact once the run has fired. So about Airflow, it's the open source leader here. You can create DAGs and you can actually run anything. It's not limited to Databricks. But it requires to be an extra service. It's an extra deployment and with maintenance. Also, it needs some expertise and to be familiar with the tool. But it has the same issues because each step here would call the Databricks API, and if you want to use a job cluster, you need to set up to pay the setup time each time. So it was an option that could not want. So what was our solution in this area? We created our own orchestration framework. We have a declarative DAG definition, and it solves our main problem that we needed a job cluster to be shared amongst multiple notebooks. So each notebook spawns multiple jobs that run on the same job cluster, and you pay the setup time only once. We have the logging mechanism in Postgres, so you have a central repository to take your logging and do your fancy things with analytics. And also you have your custom retry modes. If something fails, you can either rerun your step, you can run specific notebooks and things like that. And the dependency management was done through the jobs API. So in this area, the way forward for us is a combination of the both worlds. So on the one hand, we have our internal framework, which comes with the benefits that we discussed, and also we want to orchestrate this with Apache Airflow, which comes with its own benefits with the visualization, and also we can integrate non-Databricks steps. So what did we learn from all this? So as engineers, we can be in our pitfall sometimes and and do things for optimization from engineering, and we lose our focus. And our focus is delivering value. So always we need to balance delivering value to business with optimization and engineering things. Actually, when you deal with how you will deliver value, you can identify which are the first problems that you need to tackle and which are for later. So we have this always on mind. And also, what we showed here is that when you enter a new field, you have some low-entry options, like native CI/CD, like native orchestration. But as you scale, this is unmanageable. So you need to rework and reevaluate your low-entry options as you scale. So the mantra here is premature optimization is the root of all evil. So back to Pantelis to talk about our vision.
So for the vision part, I'm going to go back to the chart that Nico showed about DataOps. So for us, these pillars are all aspects that you will have to address eventually in order to create an architecture that scales. Okay? So in terms of data governance, we're talking about access control, lineage data cataloging, but also quality, data quality. For architecture and processes, we're talking about CI/CD and code quality. These are things that Nikos covered just before, but there's also the infrastructure. And finally, for the pipelines, we have the orchestration, again covered just before, but also the monitoring of these pipelines. We're gonna just take them one by one, starting with the data governance. So data governance, the first part is the access control. So access control is about how your users access the data. And in this two-tier architecture, anyway, this data lake architecture. There's two ways to access data. Through the metastore, so that means that we have to deal with the table ACLs and the row level access, but also directly from the storage. So there we're talking about the IAM groups and the IAM roles that needs to be set up in order to be able to be covered from all the different entry points. And why you need to do that? Because you need to keep your storage nice and clean. That's the problem of the data lakes. For GDPR purposes, and just simply if you want to make sure that nobody's going to delete your data one day. In terms of cataloging in Lineage, there's way many tools probably in the ecosystem. There's some tools that have already been there since a while. There's also tools that are developed and open sourced by big tech companies. For us, in order to address all these three issues, data cataloging, Lineage, and the access control, our choice is the Unity catalog from Databricks. Surprise. So it's well integrated with the Databricks environment. In general, it's built for the Databricks environment. It provides the data cataloging in Lineage, and at the same time, it becomes the only intermediate between your users and the cloud. That means that no user needs access to the cloud directly. They all pass through Unity, and this simplifies a lot the security model. In terms of quality, which is the last part of the data governance, quality is there for simple use cases as to make sure that there's no nulls in your data that shouldn't be there, down to more complicated use cases like detecting changes in the distribution of your data as they arrive. So depending on what you need to resolve, what you need to detect, we can talk about basic quality checks that are implemented directly by your file type. Parquet is coming with schema protection and null constraints directly. Then on top, with Delta Lake, you can have the schema evolution and the check constraints similar to SQL. And then for more complex checks, for more complex analysis on the data that are coming, you have frameworks like DQ from AWS that is open source that are doing this kind of unit testing on your data as they arrive. And then it's up to you to implement the mitigation strategy. Like, do you quarantine this data? Do you just fail your pipelines? Do you just let them pass and raise a warning? And finally, for those that work with PySpark and, or SQL directly, Databricks have these Delta Live tables that come with the expectations feature, which is like, it's unit testing, but also with all the mitigation strategies implemented. So you just set the constraints and set what happens if the constraint check fails. Next is architecture. So for that, we're focusing now on the infrastructure. So the good practice in general, not only in data, is that you have multiple environments for each team. So you end up with a big number of environments to handle. That means that you have to have an automation on the deployment. You have to be able to operate massive updates. And it's good to be able to move around, meaning changing regions, for example, within your cloud provider, or at extreme cases, just changing the cloud provider completely. So the solution on all that is the infrastructure as code. The idea is that it allows you with code to automate the infrastructure deployment and the provisioning of platform and service, etc. For us here, the choice is going to be Terraform because it's cloud agnostic, because it's open source, and because it supports Databricks since this quarter. And finally, for the data pipelines, we have the monitoring part that we owe. So why you need monitoring? You need monitoring because you want to be aware that an incident is happening, because you want to prevent incidents from happening, and because you want to be able to identify opportunities for optimization or for cost reduction. That's why we split it in three main categories. Health monitoring, that has to do with detecting job failures or detecting streams that cannot cope with the incoming data. You have the performance monitoring that has to do with underutilization of your resources or bad utilization of your resources, like spilling or high data shuffling when you're talking Spark. And finally, the cost monitoring, which is all about breaking down the cost in order to understand what spends how much, but also attributing costs to the different users of your architecture. So for monitoring, you need to collect metrics. In the architecture that we propose so far, there's 4 points that you're interested in collecting metrics. It's going to be your orchestration engine. It's going to be the provider of your clusters, Spark, your processing engine, and finally, the storage. So in terms of health and performance, there's a couple that works well. It's Prometheus and Grafana. And luckily enough, they're both integrated with Airflow and Spark. So the idea is, from Airflow, you get all the pipeline information, but also service metrics about Airflow, because it's your main, it's the center of your orchestration. If this fails, everything fails. And the metric Sparks, the Spark metrics are already available. There is the integration with Prometheus. There is a native integration. There's other options in order to just start sending data to Prometheus. Prometheus connects with Grafana, and then it's up to you to set up your monitoring, your alerting, or connect with other alerting platforms. Cost monitoring is quite simpler. This is because, at least on the Azure cloud, everything is handled by the cost analysis tool. So what is important in this part is to make sure that you tag everything, you tag your resources, and you apply policies in order to make sure that everything is tagged. And finally, in terms of storage, the monitoring should be taken into account during the design in order to have this data separation that will also help you with the cost attribution of your spending. And finally, the end game, I'm going to pass it again to Nikos.
Okay, I have talked for a lot of things here. So you have your scalable architecture, okay? That's great. We've talked about DataOps, and let's say you have set up already. That's great also. What next? Is this enough to scale your analytics? Actually, we believe that it's not enough, because then the bottleneck goes to your central data team, because your data team is exposed to many different domains, has many different customers. And if you notice the trend in technologies, if you want to scale, you need to be decentralized. So we have talked about distributed computing, we know about microservices and things like that. So the analogy here is that you can decentralize your data team, and actually this is something that we're currently evaluating. And it's correlated with the data mesh paradigm. It's something that we're actively looking, but this is a thing for another presentation. I would like to thank the data engineering team, our SRE team, and a special thanks for the support of the Databricks team. Thank you very much.